Hi guys, how's it going? I hope you guys are good. I know it's been a while. I was not available. Apologies about that. You know how life is. We can get caught up sometimes. But so what I wanna do is that I wanna try to be more consistent with this. So also I'm gonna add more of like data science problems, whereby we're gonna go through some SQL problems. Also, on adding on the data science, I would like to kind of like come up with a different approach whereby we kind of like solve a problem end to end. Let's say we're given a data set, like we go through like kind of like data cleaning, EDA, you know. So I think this way you will become more comfortable with solving data science problems, right? So on the software engineering side, I'm gonna add system design questions, like how we kind of like design Gmail, YouTube, or something like that, right? So however, if you're someone who's experienced, and you can check out my second channel, whereby I'm planning to kind of like start a series whereby I solve like real world challenges from like FAANG companies, where like let's say Uber machine learning, I read their articles and I try to replicate what they did, or I just kind of like walk you through data engineering at Uber or something like that, right? So I think this will be helpful to kind of like get you to speed, and you see how these companies, they optimize their machine learning model for production. So that might basically be good, you know. So check it out. It'll be interesting. Questions asking. So they say that we have a grid, and on that grid there's a robot, which is the starting point. So the robot is initially located at the top left corner, and the goal of the robot is to reach the bottom right corner, which is the target, right? So to get to the target, however, the robot has to take possible unique path, meaning there is a path that it can take. For example, the robot can take right, down, down. So it can take down, right. You get the point, right? So we just need to find how many possible ways, how many possible paths it can take to reach the finish line, right? So in this case, the output is 28. So we need to write an algorithm that can actually tell us that, right? So let me take you to whiteboard and kind of like explain to you how this thing works, right? So let's say we have a grid just like this, right? So this is our grid. So this is where the starting point is, and the robot is here. So you can think of this as the end. So the robot can either go to right, it can either go to right, it can either go to down, it can either go to down. That's one possible way. It can either go to down, it can either go to down, or right. So you kind of like get the point, right? So we just need to figure out how we can do this. So the first thing that comes to my mind is that, how about we treat these as rows and we're gonna treat these as columns, right? So we kind of like looking at this from a matrix perspective, right? And because if we're doing that, then if someone decide to go down, what did they do? They just canceled the entire row. Yes, they just did that because you went here, so that means you're not gonna go to this row anymore. If you decide to go down again, you cancel this row, you're not gonna go here anymore. If you go to the right, you cancel this part, you're not gonna go there anymore. So you're left with these two. So we just need to come up with an algorithm that can do that for us, right? So from a dynamic perspective, we can have an algorithm that take the row, which is represented as M, and we can also have N, which is represented as a column in the grid, right? So what we need to do is that every time we decide to go, we can think of this as down, we can think of this as right. So every time we go down, what do we do? Every time we go down, we know that we subtracting this, right? So we subtracting the rows. So we're gonna say, let's say here we had a dimension of, I'm just gonna create this, it's gonna be 2, 3. Just for your reference, I'm just going to create it here so that it's easy for you to understand. So we're going to have 2 and 3. So what does that mean? It means we have 2, 1, 2, and we have 3 columns, right? So we have 3. So represented as N, and this is represented as M. Okay? So height and width. So if we decide to go down, if we decide to move from here to here, what did we just do? We just removed this component. So we have to do that. We have to subtract these 2 by 1, because now we're going to have 1, 2, 3, right? Because that's what we just did on the grid. So we continue with the algorithm, right? This is going to be done through recursion. So if we decide to go again to the left subtree, so we're going to have to subtract this 1 by 1. So this is going to give us what? It's going to give us 0 by 3. So what does this tell us? It tells us that we went outside of the grid. So this is good for us because we know that this is going to be a base case. Okay, so when we reach a base case, we're going to have to return 0. Why are we returning 0? Because there is no possible path. We went outside the grid. So where we get 0, it's not good. So it's outside the grid. But we took down, but we have another possible choice that we can take. What is that possible choice? It is right. So we know that if we decided to go to right, then we have to subtract the column, not the rows, because the rows is still going to be 1. So we just have to subtract the column. So this is going to be cancelled out. So it's going to be 1 by 2, right? So this way it's still valid because we only left with these 2 component here. We left with 1 and 2. That's it, right? So if we decide then to go to the down, there's no way we can go down. There's nothing inside here. So there's nothing. We're going outside of the matrix. So it's going to be 0 by 2. So this should return 0. So this is also our base case, right? But if we decide to go right, what will happen is that now we're going to remove this part. We're going to remove this part. We're going to be left with this. So what does this mean? It means that we're going to have still 1 row and we're going to be left with 1 column, because this is the only column that we're going to have. So it's going to be 1 by 1. And you realize that, right? We're at the end. So this means that whereby we see that our row and column is 1, this is a base case, right? Meaning that we have to return 1. Right? We're going to have to return 1. So we're done. So what does this mean? It means that from a recursion perspective, this is going to return 0 because we just returned 0. This is going to return 1, and we have to add up all of these things. So both of them, as we add up them, they're going to return 0. Similarly, this is going to return 0, right? Then this is going to be 1. We add up 0 plus 1 is going to return 1, and at the base case we're going to return 1. Then we have a red subtree to kind of like traverse through. So what does this mean? It means that we can take down, we can take right, and we can take right, which makes sense because it is, think about it. We had this, right? We had something like this. We can take down, we can take right, we can take right, which makes sense. We said down, we said right, we said right. So these other ones, they don't exist, because if we follow this one, let's follow this one. We had down, we had down. If you go down, you go down, you're going outside of the matrix. That's why we decided to return 0 there, right? That's how it works. But however, as you know, we're going through each we're going through each combination. So this is the term complexity of this is exponential. So we're gonna have it's gonna be an exponential term complexity. So what we can do in this case is that we can use a normalization to move from exponential, and we can probably say we can visit n times m combination, right? So we can move from exponential using a dynamic solution like normalization. That's what we can do. So if we add a normalization to the solution to say, if we know that this combination of 1.3 is going to lead us to 1, then we're just going to cache this in the memory. So we don't have to like kind of like go through and do the calculation for that. But I'll show you in the code how we're going to go about that. Okay. So let's get into the code. And so the first thing that we're going to do is that we're going to start with our base case, right? Like, let me see. So we're going to start with our base case, which is m equals to 1. I think m equals to 1 and n equals to 1. So we know that when these two are equals to 1, we have reached the end, right? Even if it makes sense, because even if we have one element, one row, one column, we have one element, that's the end. Like return 1, it's fine. So it's a good base case. So if we have m equals to 0, if any of this, because we know that 0 represent we're outside of the grid, so we're just gonna return 0 in this case. Okay, the last thing that we need to do is that we need to then do a recursion to go through we go through like each possible ways, right? Like, you know, like I explained that we need to like kind of like, if we decide to go down, then we need to subtract from the rows. If we go like, you know, right, we need to subtract from the column, right? So we're gonna say self, we're gonna call the function itself, just gonna, you know, copy and paste. So we're gonna call this function and we're gonna pass it, we're gonna say m minus 1. As we go through that, we're gonna subtract that and we're gonna add self dot, and we this time, because we're gonna go down, we don't have to subtract from the rows, but we have to subtract from the column, right? That's how it works. So let's give it a try. Let's see if I missed something. Oh, I made a mistake, sorry about that. I see my mistake, it's here actually. I wrote n, so whenever n equals to 0 or this, yep, now I think it's looking fine. However, like I said, this is gonna give you an exponential, so it might not be accepted in an interview because it's not efficient solution. So what you need to do is that you need to come up with this memo, then you need to come up with your own key. And please note that coming up with the key is very important, because how you select your key is very important. For example, if we can have 4 2 3, and we can also have 4 2 3, right? If you're gonna do something like this, whereby this represent your rows, like it represent m, and this represent n, this represent m, this represent n. If you're gonna say this is your key and you don't include something that separate m and n, then these two combination will be considered as one thing, right? So it's important to kind of like, as you create your key, make sure that you have something that kind of like separate them. So for example, in Python, we can probably use a string function. We can say key equals to f, and whereby we can say m, then we can, you know, separate them by underscore, and we can do this. So this is fine. So we know that they are separated by underscore, so it's fine. So what we need to do is that we need to say if key in memo, then we just need to say return memo and key, whatever we stored in the memo for that key, because we don't want to repeat that. We don't want to do the calculation. And how does that results get into the memo? We just have to say results equals to the results that we're gonna get, and we just need to say memo key equals to results, and we just have to return results. Okay, looking good, right? So what we say here is that every time we get the results, we're just gonna cache them. The reason we cache them, like I said, is because we don't want to repeat. As you can realize, if you can take this path, you can take this path, they're gonna lead to the same thing. So there is no need. If someone take this path, they're gonna lead to the same thing. It's either you go there or you either go there. So we don't want to repeat our recursion. So it's a very efficient way to move from exponential, right? So let me just run the solution and let's see if, so I'm just gonna submit. So I'm just gonna go to the second problem. So it works and it's very efficient, right? So let's go to the second problem now, which is unique path 2. So I'll say like this problem is still literally the same with the problem that we just did, right? They are literally the same. It's just that this time we are told that like there's a blocker. So what do they mean? But when they say there's a blocker, they mean that if there's a blocker, then you can't take that, you can't take that path. So let's go to the board and try to explain this, right? So we know that we have something like this, right? We know that we have a grid like this. So there's one here, which they say if you face one, that's a blocker. That means here you're gonna have zeros, right? It's gonna be zeros. So it's still the same thing whereby we just wanna reach the end, but no, here's the start. It's just that now we have this one. So when you have one, you can't take that path. It's a blocker. So what it means is if you try to do something like right down, it does not count because there's a one, so it's not a path. So you have to return 0. So the only way you can go to the end is if you go to right, down, right? That will count because you did not come across one. So what does this mean? It means that we're still going to do the same thing. It's just that now we just need to take this grid. Let's say they call it obstacle. They call this grid obstacle. Then we just need to say where M, which is represent the rows, maybe this row, and we're going to say column, which is represented by N, equals to 1. So where a cell equals to 1, then we want to return 0. That's it. That's the only thing that we need to do. Then we're done. The only thing is that I'll explain to you. The only thing I'll say, it's just being careful around the indices, but we're gonna look at that now. So okay, cool. We're gonna go with this, right? So the first thing that we're gonna do is that we're gonna try to get the rows and the column. So we're gonna say obstacle grid, which is this. Then if we can say length of this, it's gonna give us the number of rows. So if you say length of this obstacle, so it's gonna say 1, 2, 3, right? But we know from Python that we want to start from 0 to 2. So what we can do in this case is that we can say -1, right? Because this way we know that if we go into query this, it's going to be much easier. And this is very important because previously when you were given these indexes differently. So that we're given them as 1 and but we want to start from 0. So it's very important to kind of like note that distinction, right? So the column, to get the column, you're gonna get the first row because it's gonna be 0, 1, 2, 3. So which means that to get the first row, you're just gonna have to say length, give me the first row. And we also have to say -1 because we want to start from 0 to 2. Okay, so this is very important. So that means our logic will kind of like, our conditions are going to slightly change, but overall everything should be the same. So I'm just going to create the same algorithm and I'm going to call it unique path, whereby I'm going to take M and N and I'm going to pass it the memo, for efficiency, and I'm just going to create the same key just like we did, which means that I'm just going to take M underscore N, close it. Oops. Okay, perfect. Right, then I'm just gonna ask, like it's memoization is something that we have to do to make to make this the complexity of this function. So if key, sorry about that, if key in memo, then we just need to return memo key, the results that we stored in memo. Okay, so the first thing that we're gonna do is that we're gonna say if M, so this is where I think the differences are because of we're using different indices. So you just need to say if M is less than 0. So remember that previously we said equals to 0, but because of the indices, like I said, we're starting from 0 to 2. That's how Python works. And because if we didn't do this, then we won't be able to query the grid. I'll show you in a minute, but this is important. So we have to say M is less than 0, or I think we can do this in the same thing, or n equals less than 0, then this is where we want to return a 0 because we're going outside of the grid, right? So if it happens that we have so this is where I wanna query the grid. So for me to query the grid, I'm gonna need an obstacle, this. So I'm just gonna say where m and n, meaning a specific cell, is equals to 1, then I also want to return 0 because it's an obstacle, like, right? Okay, then we can do the same thing. We can say now we're gonna, instead of saying equals to 1, we're gonna have to say equals to 0, if that makes sense, right? So m equals to 0 and n equals to 0. So why are we doing this? Unlike previous question, these elements were given to us, right? They were given to us. That's why we had to kind of like say m equals to 1. This time we have to say equals to 0 because of how we indexing them. If we didn't do this, then we were not going to be able to index the grid. It was not going to be possible, right? Because we were going to go outside of the grid. So we were going to have an error. So that's why this problem also requires us to kind of like rethink how we indexing the grid. And if that makes sense, right? So we're going to say m equals to 0 and n equals to 0. Then we're going to have to return 1. Then we fairly do the same thing, right? We're going to say results, which is going to say unique path, call the function, which is going to be path. Then we're going to pass in m, and we're going to pass in the memo. But as we know, we're going to subtract the m. Then we're going to add, just copy this. It's going to be the same thing. We just need to subtract, like down and go. We just explained this, right? Down, right, that's how it goes. Oh, it's gonna be subtract -1 and -1. I think that's all for now. I hope I didn't make any mistake. So I think that's all we have, which is gonna be m and n. So that's the solution essentially. Here we're just doing a recursion. Unique path is not defined. Okay, cool. I think I forgot to put this into a memo. So it's gonna be memo key equals to results, right? Like I said, we need to cache this, and obviously we need to return this. But this is like me trying to like cache the results so that we kind of like don't have to go through this again. Yeah, let's try to submit this and see if it can work. It worked, so we're good to go. So that's the solution, guys. I think you can try it out. I'll just copy the code in the I'll just post the link of the code in GitHub. So thank you guys for tuning in. See you guys next time.